Okay, I'm going to go through some questions on forces at GCSE level. This is a practice exam I'm going to do with the model answers, and I'm going to talk you through how to read the questions and also to how to approach an exam with the best communication skills possible, so you won't miss out on marks as you're preparing for your GCSE in your own schools. Okay, so this is a practice test I'm giving my students, and they've just completed a GCSE level course on forces. So the first question, this is question 1. I've just printed these. These are AQA exam questions, so they're good for practice for whichever board you're doing. It says question 1, the distance taken for a car. So first thing I do when I'm reading it is I'm making sure I'm taking the information in. The distance taken, and it's a car, to stop after an emergency. It depends on two things, and they tell you what the two things are. So they're giving you information before the question: the thinking distance and the braking distance. So if you've revised, you'll know the thinking distance is how far the car travels, while the driver processes the information, which depends on reaction timing. Okay? What factors affect reaction timing of the driver? And the second one is the braking distance, how far the car travels after the driver reacts and brakes to whatever the emergency might be. Okay? Now different factors for different things. So they're giving you the information, now they're giving you a question. Each of these distances, each distance, they mean the braking distance and the thinking distance before that, is affected by different factors. Okay, so they want you to tick the boxes. Where are the boxes? Here are the boxes for thinking distance, braking distance, or both, to show whether each factor, and the factors are shown here, affects the thinking distance, the braking distance, or both of them. So for the speed of a car, the first thing is with the speed of car, obviously if you're driving fast, while you're thinking, you're going to travel a further distance, so it affects this one. It also, if the speed of the car is higher, the brakes have to work harder, so it will take longer for them to be able to work against the kinetic energy of the car. So both of these are affected by the speed of the car. So you can just tick both. Water on the road doesn't really affect your thinking distance, but it does affect your braking distance because it makes the road more slippery, so there's less friction between the tire and the road. So be careful when driving in wet or icy conditions. The driver's tiredness, well, that will affect his mental faculties, so that's his thinking. It doesn't really affect his braking. He'll be just taking longer to activate the brakes. So you just tick the thinking distance box. And the driver's alcohol consumption, it also affects him mentally. It doesn't affect the braking mechanism of the car. And the conditions of the car brakes, well, that's obviously only going to be affecting that. So you get 2 marks, and if you got all 5 ticks correct, you'll get both marks, and if you've got 3 or 4 ticks correct, you'll get 1 mark. So that's how they're going to give you the 2 marks. So these are a nice, quick question to start you off. Okay? Over the page, it's given you a graph, and it tells you what the graph is about. So figure 1 shows part of a displacement time graph, and it's a car journey. So remember, displacement is a vector. It has the distance in meters, and the direction matters because it's a vector quantity. So you have to remember what a vector quantity means. It's a vector quantity means size, magnitude, and direction are important. The x-axis is time in seconds. Whenever you do graphs, don't forget to label your own axes. It then says complete the gaps with the letters from the diagram. So you've got to complete the gaps. They've given you gaps in these questions with letters from the diagram. So A, B, C, D, E, F, or a combination of. Okay, so the first question is asking about the car was moving forwards. Well, forwards means started from 0, so the 0 displacement is here. So forwards would mean the outward journey, so the forwards would be upwards on the graph. So forwards will be upwards on the graph. So where is it going upwards? Going upwards from A to C. It then stops going any further upwards. So the maximum displacement would be here around the level with C. Okay, so the car was moving upwards or forwards between A and C. And that is the answer they're looking for. The car was then stationary from C to D. How do we know the car is stationary? Stationary means on a displacement time graph, it will be a horizontal line. Okay, so this stationary means it should be a horizontal line. So the answer will be between C and D. It's not moving. Okay, and then it says the car is moving slowest between which two? Now, slowest, obviously it's moving slowest when it's not moving at all, but they think they mean when it's not stationary. So that's not completely clear. So the answer they're looking for is the least steep line. So you have to use your judgment here. So the least steep line to me looks like B and C. Yeah, but I bet you some students will put C and D, which technically is not incorrect. So 1 mark for saying B and C. And then for the next question is the car was moving backwards. Well, backwards, if upwards is forwards, then backwards must be downwards on the graph. That means coming back home. So this is the outward journey, displacement increasing, and from D to F, the displacement is decreasing. So it's going to be from D to F. And that's how you get the 4 marks. So they're the 4 marks for the first part of this question. Just get my red pen out. So you get 1 for A and C, 1 for C and D, 1 for B and C, and there's your 4 marks. Okay, the question is then goes on to 1.3. Just move the paper so you can see it clearly. And it's now asking you to tell us, again, it's a vector-based question. What is the difference between speed and velocity? So they want you to know the difference between vectors and scalars. So once again, vectors have directions, scalars only have size. So vectors have size and direction. So speed has size, velocity has size. Speed has no direction, so it's just how fast you're traveling. Velocity, you need to mention the distance, the direction as well. Same as with displacement we just did. So scalar is speed and vector is velocity. So 1 mark for getting the column under speed, the 2 ticks correct, and 1 mark for getting the 3 ticks under velocity correct for your 2 marks. Okay, that's 1.3. The next question then is 1.4, and 1.4 is about a velocity time graph. This time you've got to draw it. Well, they want you to draw what it means. Just getting my ruler. They want you to move at a constant velocity. So if it moves at a constant velocity, what does that mean? It means it must be a horizontal line. Because if it's constant velocity, it's a velocity time graph, the y-axis value mustn't change. So there's constant velocity. Okay. Then On the scale below, or axes below, draw a velocity time graph for a car that first moves at constant velocity. That's how I'm reading it. Then it slows down. Well, slow down means the velocity should go decreasing, so you want a downward slope. Yeah. And then I'm reading the question. It then stops. So if it's got a downward slope, nothing happens in between, so it just reaches the zero on the velocity time graph. So it moves at constant velocity, so this is a decreasing gradient, a decreasing slope. The velocity is decreasing, so it's a negative gradient. These are the points that you need to make sure you know for the exam. And then it stops. That means it must reach zero on the velocity axis, reaches zero. Okay, so I'm assuming you'll get 1 mark for each of those lines. So horizontal line, decreasing and finishing with 0. That's your 3 marks for question 1.4. Okay, that's question 1 complete. Question 2 is about Hooke's law. So the student wants to measure, it says, the student wants to measure the spring constant of a spring. So this is investigation skills they're going to test you on. I gave my students a 35-point checklist to help them practice investigation skills, and this experiment is about Hooke's law. So you need to know that Hooke's law is F equals kx, where F is the force you apply, which this will be the force, is the weights you're adding, and the extension is how much the length changes as you're adding them. So the equipment is shown here. They put the spring with the weights on it, stretching it, so extending it. So x is the extension. So they've put it so 0 is here, and that's one of the first questions. So this will be the starting position before it's stretched. So this is starting positions, that will be the original length. The equipment she uses is shown in figure 2. The scale measures distance. The scale measures distance in centimeters. So these numbers in centimeters. Okay. So we have to move it up. Hope that makes sense. So we need F equals kx. No, it's Hooke's law, and we want the spring constant is the value k, which is the proportionality between the force and the extension. So the stiffer the spring, the more force you need to extend it the same amount. So the first question then says, explain why the 0 mark is slightly below the top of the spring. Because the top of the spring, you want to measure from the bottom of the string how much is extended. So that would be, I'm assuming that would be the starting position of the spring. So you need to make sure you have answered it exactly how they want. So going back, you can see where the 0 is. So that would be the bottom of the spring. They've adjusted the ruler to make sure the 0 value is at the bottom of the spring where you're measuring from, and they've put a pointer. They've put a pointer to the bottom of the spring. So before you put the weights on, the pointer would have been pointing at the 0 mark. Okay. So basically, once you read off this scale, you'll automatically get the extension. So explain why the 0 centimeters is slightly below the top of the spring. So I would write to allow for the size of the spring, which will then enable you to measure the extension of the spring accurately. If you don't set it as and take into account the original length of the spring, you won't be able to get the accurate extension. So it then says, as the student carries out the experiment, her head moves slightly up and down when taking the readings. And then they want you to know the type of error this movement would have caused. Well, it's kind of this, how would you express this if you haven't been taught it? Okay, I'm not sure I taught my students exactly what it's called. Well, this is a kind of error. This is a random error, because if her head is moving up and down, so once it could be too high, the reading, or next time it could be too low. There is no systematic way of telling whether she's doing all her readings from a too high a position or too low. Really, you want to get down to the level to reduce parallax. And if you're moving your head up and down to reduce parallax, that's what the tennis judges do. They make sure they're in line with the white lines on the tennis court. Okay, so this kind of error is called a random error. Okay, that's question 2 done. Okay, and now we're going to the next part of question 2, which it says, how does the pointer make the measurement more accurate? Well, that's what we were talking about before. So if you look at the pointer, yeah, it allows you to get rid of the parallax errors. A bit like tennis judges, it allows you, it's easier to read the scale. I gave my students set squares, which are those triangular rulers where they could put it where the bottom of the spring was at right angles to the ruler. So this is the right angle side of it, so they can make sure that if their spring wasn't quite against the ruler, which isn't always easy to do when you're doing it practical, to be able to make a better judgment and make it easier to read. So this will create a smaller parallax error, or reduce the parallax error, the chance of parallax error. Again, that's why the judges sit there. Okay, the next bit I've already written out for you to save time, because the next bit is a long answer. It's 4 marks. Okay, so explain how the student could use the equipment in figure 2 to measure the spring constant. So again, I was telling you the spring constant is K. They want a descriptive answer, and you've probably already started reading my answers. Okay, so K is the stiffness constant, F is the force that you use, which was the weight you added, and X is the value on the meter ruler reading that they put to the side where the pointer is pointing. So how do you explain that? So I've just put the theory first. I've said, well, the spring constant is K in the Hooke's law equation. So I think that's useful to make sure the examiner knows that you know what you're talking about. And the rest of it is clarity of your communication skills. And a lot of physics actually is clarity in English. So take readings of force and measure or record the extension or length each time. My students did length each time, and then they took away the original length. So they, as long as you're communicating that you know how to get the extension. But remember that extension is the new length minus the original length. Okay? Now in this experiment, they put the pointer, so it started at 0, which would have indicated 0 would have been where the original length was hanging from. So they wouldn't need to do this. So I've put it in brackets. in case my students say that, and I would give them credit for it. Once you have sufficient readings of force and x, so I've already defined force and I've defined x as extension, plot a graph of F against x, and if you do that, you'll know that up to the elastic limit, you'll get a straight line graph. And the gradient of that, so delta F over delta x, the ups over the longs, as they say, this will give you, should get a straight line graph. The gradient is the spring constant, okay? So I don't think you have to calculate it, you just need to explain to the students how to calculate it, okay? So how does that give you 4 marks? The mark scheme says a detailed and coherent description of how to measure the spring constant, and it includes multiple measurements and use of the gradient. Well, we got the gradient and sufficient readings of F against x, so we have those 2 conditions, and we have a coherent description. So I think this will get you the 4 marks, because I don't think there's anything missed. Okay, so this is smaller parallax error above. I'm just putting the tick for easier to read or smaller parallax error. Both of those will get you the mark for those questions. Okay, now the next part is complicated because you need to do some calculations. So you need to make sure you know which equations to use. So it says the student found that the spring constant was 15.6 newtons per meter. So that's K. So remember, K is the stiffness, the gradient of the graph which I've sketched. Calculate the extension of the spring if the energy stored in it was 1.9. Now remember, energy stored is the area underneath that graph. Okay, well, this is a triangle, so the area is half fx. Okay, but we don't know the F. We haven't been given that. We've only been given the energy stored. So we know 1.95 is that area. So we could write that the energy stored is equal to half fx. Now remember that you also know that F equals kx. Now since we don't know F, you've got to use your mathematical skills to replace F in the equation with kx. That means that energy is half kx times x, which equals half kx squared. We know k is given to us here. We know E is given to us here. So, and we know obviously half, so all we've got to do is work out x squared. Okay, now the units are in newtons per meter, so don't get fooled by that. So it follows that since energy equals half kx squared, you can just put the numbers in. If it helps you, a lot of students prefer this method, 1.95 joules, and we don't need to look at that, we're going to go straight to this side. Half K, 15 times 15.6 newtons per meter, multiplied by x squared. So the only thing we don't know is x squared. So that shows they haven't really left a lot of space in the printout that I've got for this paper. So I'm going to go in a straight line. It follows that x squared, well, half times 15.6 is 7.8. Yeah? That means x squared equals 1.95 divided by 7.8, and that, I think I did it before, it comes out to exactly 0.25. That means that x is the square root of 0.25, which is 0.5, and don't forget he was doing it in meters and they want it in centimeters, so that's quite a complicated question, and you need to make sure you know about energy and you know about combining equations from your math skills. So 0.5 meters you would put as 50 centimeters. So how did they divide up the marks? Let's have a look at the mark scheme. The mark scheme says as long as you got to this point where you've put the numbers in, so you kind of got to this point, that's the first mark. You put the 1.95 in and you worked out that you've got to combine the equations. Second mark is for doing up to here, either of these. So either you've done this equation here or you got 0.25 correct. And finally, for changing it to 50 centimeters is your third mark. I think that's quite a tough question for 3 marks, especially if you're new to GCSE. Okay, so that's 2.5 done. Over the page, we're on question 3. Okay, and question 3 has another part to it, just making sure I have the other part ready as well. Okay, so question 3 is about a jetpack. You've probably seen these at some point, and it says, figure 3 shows a person using a jetpack, a device called the jetpack. Water is forced downwards, so the water is fed from the machine, so it sucks water in here, it then forces it out, so it's a bit like a rocket. So my students actually did an experiment with rocket power, and they know that this is to do with Newton's laws. Okay, water is forced downwards here, so the water is forced down at velocity from the jetpack, so the jetpack's on his back, and he's stuck to the jetpack, probably with a harness, and this produces an upward force on the person. So force downwards on the water, the jetpack kicks the water out, and that produces a force upwards. Now how are you going to put that into words? So that force upwards comes from Newton's law. Which Newton's law is it? It says explain why the jetpack moves upwards. Yes, there was the jetpack and the person when the water is forced downwards. Well, that's Newton's third law. I've already put it in brackets. I always do that when I read questions to prepare myself mentally for what's coming. It says include reference to the relevant law in physics. Well, there you go in your answer. And I've said this can be explained by Newton's third law. I would say that will get me a mark just for saying that. If the action in Newton's third law is the jetpack forces water downwards, the reaction will be so that the water exerts an equal, just need to move it up, sorry about that. So the action is jetpack forces the water downwards, so they're actually giving a mark just for saying that. Okay, but the water is forced downwards is already in the answer, so I think that's a bit generous to give that second mark. The reaction will be, every action has an equal and opposite reaction, that the water then exerts an equal and opposite force on the jetpack. Equal and opposite, so it's magnitude and direction, force on the jetpack. So I think that's how they divided up the 3 marks in the exam. So I think the second one is very generous, as it already says the water is forced downwards. Okay, so if the water is forced downwards, then the water creates an equal and opposite force on the jetpack, so it moves upwards. You don't need the bit in brackets. And when you're looking at just the jetpack and the person, which are the same person, then the acceleration will be upwards on the person. Once that happens, you're analysing one of the objects. You're no longer interested in the water. You just know that the force upwards created will be by Newton's second law, and this becomes F equals ma. Okay, so that's 3.1. And then finally, they finish off with a mathematical analysis of the situation. So it tells you, read the following information. So what I do is I make sure I'm active when I'm reading it. And when I'm reading it, I put the letters in, so I'm making sure that I know which letters they're being used. Combined mass of jetpack and person, together they weigh 84 kilograms. So that automatically tells me that we know the weight. Okay, so then it says the upward force from the water is 1900 newtons. So that's from Newton's third law. 1900 newtons upwards, and you've got the weight downwards. So you have to work out which is bigger. If the weight is bigger, they'd fall. So I'm assuming the weight will be smaller than that. So we'll get to that. I think that's the first question. Starting velocity, normally we use the letter U. It's become a bit unclear in my scribble. Let me just write that again. So that's equal to U, the initial velocity, or the starting velocity as they called it here. So, and then the acceleration due to gravity, G, they're given as 9.8 meters per second squared. In some exams, that is rounded up to 10 meters per second squared. Okay, but if they're giving it to you as 9.8, you use it as 9.8. So we have that. Then it says calculate the maximum speed. Well, if the starting speed was U, the maximum speed will be after the acceleration takes place due to the difference in the forces. Okay? When the person reaches, let me read that again. Calculate the maximum speed V the person reaches after moving 5 meters upwards. So the letters we use are SUVAT, V, U, A, and S. Okay, as well V, U, A, and S. And T is not needed in this equation, so we're not using time at all. So first of all, it says calculate the weight of the jetpack and the person. Well, the combined mass of the jetpack and person is 84 kilograms. And I put the equation you need to use here, which will feed our force diagram. So it says use two significant figures at each step in your calculation. So show you're working. So the first thing they want you to do is W equals mg, which is equal to 84 kilograms times 9.8. And that's why exam boards often give 10, so you don't have to waste time with the calculation. If you multiply those two numbers, it's 820 newtons. And that's again to two significant figures. So it may have been 820 something or whatever, but you only need to put the first two significant figures. And that's a skill in the exam, to know how many significant figures to include. Don't write what you see in your calculator. It then says calculate the resultant force on the jetpack. So on the jetpack is using the water to force up. So this is the water force upwards, and the weight is forcing it downwards. So the resultant force is the unbalanced part of that force, will be equal to 1900 upwards. So it's going to be upwards because we just worked out that the force downwards, W, is 820. They want you to show that the result, you know that it's going to be 1900 and minus 820. So that's going to give you approximately, remember they want you to do it, you can ignore the 2, because it would be less than that to two significant figures. Yeah, it's actually 1080, but you round it up to two significant figures at each step in your calculations. So make sure you're following their instructions. Once you know the resultant force, I'm just going to move it upwards. Then the resultant force is to calculate the acceleration. You now need to know Newton's second law. We know F equals ma is Newton's second law. Okay, so now we want to work out acceleration. So this follows that acceleration is equal to F over m. Yeah, if you don't remember how to do that, you need to make sure you remember your triangles. So F would be at the top, m and a would be at the bottom. You put your hand on the A, it's F over m. The unbalanced part of the force is 1100 newtons from part 2, 1100. Divide that by the mass, which was 84 kilograms, and that gives you, to two significant figures, approximately 13 meters per second squared. So the acceleration is 13 meters per second squared. So we've done the weight, we worked out the resultant force, we now calculated the acceleration. They now want you to use what in my class there's one student who doesn't like this equation, so she's now hopefully revised it and become more familiar to it. So they want you to use v squared equals u squared plus 2as to calculate v. So we know u is 0, yeah, from the question information given, u is 0. We know a from the question given, so we know a, we know 2, and we know s also from the question given, so we know everything apart from v. So they want us to now use that. So we have to use v squared equals u squared plus 2as, and that's equal to 0 squared plus 2 times 9.8 times s, which in the question above is given here as 5 meters. So you multiply that by 5, and it's as simple as that, and then you work out what that is. So 2 times I'm using the wrong acceleration. The acceleration is the value we just calculated, not gravity. Of course, it's accelerating upwards, okay? So the acceleration upwards is 13 meters per second square, so be careful you don't make a silly mistake like me. So you got 13 times the 5, 13 times 5 is 65, 65 times 2 is 130, so all that equals 130, but that's v squared, so v will be equal to the square root of 130, square root of 130, to two significant figures. The closest is 11, not 12. 11 meters per second. So it's going to be somewhere between 11 and 12 if you do it to three significant figures. But again, remember, they told you just keep it to two significant figures. And if you don't do it to two significant figures, you will lose some marks if they've told you to do that. So we had 820, two significant figures, 1100, two significant figures, unbalanced force, then calculating the acceleration as 13, but you also have to change the equation round. So I think they've given you a mark for the answer and for doing this triangle, knowing which way to rearrange the equation. So 1 mark for doing the rearrangement with the numbers in, and 1 mark for the answer. And then the final one, putting the numbers into the v squared equals u squared. So I would have lost a mark there if I hadn't noticed I was using the wrong one. So it's going upwards, the acceleration is upwards, and the answer would be that it would reach a speed of 11 meters per second. And you're meant to put the answer in the space provided at the bottom. So I'm just going to put an arrow there to show where I got my 6 marks. And that is the end of this practice exam. I hope you found it useful. I'm going to upload this to YouTube for you. If you want to know when I do another GCSE practice exam, then please subscribe, share the video with your friends if you want to, and please like it and leave a comment if you have any further questions. Thank you very much for watching. Bye for now.